To understand Bayes' theorem properly, to derive it and to use it, we need to understand theory of total probability. Now, what does the theorem tell? Total probability theorem is all about adding up different routes to the same destination. Not theorem, total probability, something to do with total. Let's understand this. A factory has 3 machines, A, B, C, that produces a certain product. Okay. The probability that the machine A produces a defective item is 0.1. So this produces an item which is kind of bad, and that is around 10% of the products. Machine B is around 0.2, and the probability that machine C produces defective ones is 0.3. What is the probability that a product selected is a defective one? So whatever is being produced over here, right? They're put in a single place. They're stacked up. So if you happen to select one of it, so maybe this one is defective, that one is defective, so on and so forth. So if you happen to choose one of it, what is the probability that this is a defective one? That's the question. Okay, so that's why the total probability. So we are taking not individually what is the defect, what is the overall contribution of it, so it's something like that, right? So the total contribution and how they are related, and how is an overall, how many machines or how many products that we get it right and how many products we don't get it right, and so on and so forth. And we choose one of it and it happened to be defective or not defective. All that can be done with the help of total probability. So let me put it in general. So this is the proof. The statement begins with let E1, E2 and En, so on and so forth, be the portion of the sample space S, right? So these are all the items that is produced by different machines. So there are n number of machines, and these are all the items that is produced. So this is the sample space. And suppose that each of the event has non-zero probability of occurrence. So everyone is producing a machine. Now let A be an event associated with S. So let's talk about a space, say it's a big space, and all of this is event A. That is, each machine is contributing different amount to this event A. It might be defective, it might be a product which is unique, so it can be anything. This event can be anything. So this entire space is dedicated to event A, contributed by different machines. Okay, so let's derive this. I would not show you guys a final answer initially, as and when we derive, it will build up. See, first thing is what E1 does is not dependent on E2. That is, E1, E2 are, all of these are disjoint. So the union of this, all of this machine, will lead to S, and also, right, all of this output by all the machine will give us the sample space, entire sample space. And also EI intersect EJ is a null set. They are disjoint. For I is not equal to J, right? So, and I and J belong to N. That is, E1 is not equal to E2, E1 intersect E2 is null set, E1 intersect E3 is null set, so on and so forth. All the combination. So there is basically no overlapping. So basically they are disjoint. So it's a way of talking about disjoint. It's only for your understanding that I'm writing over here. It's a way of talking about disjoint. Okay, next, let's talk about A. A is part of S, is it not? So if I take the intersect between A and S, I'll get A. Now, but S itself is a huge thing. That is, it is made up of E1, E2 till En. Using our distributive property, I can rewrite this as A intersect E1 union A intersect E2 union and the last one is A intersect En. Right? I can do that. Now, so we have A intersect E1, comma, so on and so forth. Right? All of these items are subsets, is it not? Means what? They're part of A intersect E1 is part of E1. Right? Obviously, right? If this small space is where E1's contribution to A is. This entire space is E2's contribution to A. So end of it, all these are what? Subset. So with this, what can we infer? A intersect E1, comma, are all disjoint, right? Agree? So why is that I'm talking about disjoint? Well, now I can talk about probability of A, which is probability of A intersect S. And with all of this, what can I tell? That it is probability of A intersect E1 union A intersect E2 union union A intersect En, closing the brackets. Agree? Right? So what are we looking at? We're looking at making use of, what is it? Yes, E1 plus probability of A intersect E2 plus, that is, since they are disjoint, I can do this, right? Basically, I'm using A intersect A union B's probability plus probability of A intersect En, and there's no minus because they are disjoint. Is it not? We are basically using the A intersect B formula, sorry, A union B formula's probability, but applied to n number of terms. Okay, so we have seen this. So we see this in your 11th grade, right? Over here, this is basically this. Actually, for disjoint, this is a formula, right? So we are making use of that. Okay, or is your union, and that's what we have over here. We're just making use of that. And this in turn can be written as what? Probability of E1 into probability of A given E1 has occurred, right? Probability of E2 into probability of A given E2 has occurred, plus probability of En into probability of A given En has occurred. And so in general, it is probability of EI, not En, EI into probability of A given EI has occurred, where I will run from 1 to n. Is it not? So where is that? What is that we are talking about? This is from your multiplicative theory on probability, right? So this is from your, you guys have to multiplicative theory on probability. Okay, so yeah, basically what is that we are trying to tell? We're trying to tell that each of these events contribute to A, and all of them add together will give us A. Contribution of all of them are added together, right? It's in a simplest manner, it's that. But here we have a bit of complicated probability version, but it means the same. So basically, E1 happening and it leading to A, E2 happening, it leading to A, so on and so forth. So if you add up all of this, I'll get the probability of A itself. Right? Again, it goes back to the first example. All of this machine's output, they add up, they bundle up, and the product as a whole is stacked together. Make sense? So the fundamental idea is about totaling up the contribution of different things, and it's related to probability. Okay, so pause, copy everything, try to even copy the formula, sorry, not formula, the example and the diagram, and then the derivation as well.